I think we will start this class on electrical propulsion. When we said propulsion and we consider different forms of propulsion, essentially chemical, inert gases and stuff like that. When we use electrical power for pushing, we say electrical power, because propulsion we said comes from the Greek word propelleri, meaning pushing forward, and we use electrical energy for pushing. I think we must be a little bit clear about how we can do it using electricity, and therefore whenever we say electrical propulsion, let us go through the basics and see whether we can understand something about propelling in some way. I go back a little bit, ask myself one question. I say we talked in terms of let us say gravitational field. We covered this, we started with this. In fact, we said planets are moving, Newton saw the movement of the planets, he saw an apple fall, he formulated the universal law for gravitation, which was minus g into m1 m2 by r squared. If I want to put it in terms of the direction, I put vector here, I put a cube here, and then I put the vector over here, right. This was the universal law for gravitation, and the gravitational constant we saw was 6.671 into 10 to the power minus 11, right, and the units were Newton meter square by kilogram square. Why am I talking in terms, what is gravitational field? When a mass is up there, maybe on the surface of the earth, it is pulled with some field, or rather I can put the mass of the earth here and then mass of the body which is on the surface of the earth or somewhere, and I substitute the radius of the earth to denote this, and I get the value F is equal to minus mg, and this g is what you call as the gravitational field. Force is a vector and the vector comes from this, right. Therefore, you see there is a field, a vector field, which attracts the body and gives weight to the mass of the body. In other words, force is in Newton, mass is in kilogram, g was in meter per second square, and therefore it is loosely talked as acceleration due to gravity, but there is no acceleration involved, it is just a field which is available. Therefore, just like we talk in terms of a gravitational field, can we think in terms of other fields, especially coming from electricity or in some way magnetism or stuff like that? We can talk in terms of maybe an electrical field just the same way as a gravitational field. We can talk in terms of a magnetic field. Are there any other fields we can think of? Maybe we should spend some time when we review the whole things what we have studied. Maybe some people talk in terms of Casimir forces, some other forces, they say the 0 degree Kelvin dark matter which is available in space is capable of doing some work. What are these fields we are talking of? Maybe we have to review it in some way, and since most of us are in mechanical and aerospace and our basics in electrical engineering is might be somewhat rusty, I thought let us go ahead and look at the units. Let us try to see what a electrical field could be, what a magnetic field could be, whether we could use it in some way to push a rocket, and that is what I will be doing in this class. And while doing so, in the same way we derived propellants, chemical propellants have these characteristics, a low molecular mass, a high temperature is what we require. Can we put some requirements for things when we want to push something using electrical and magnetic fields? That is what I will be doing in today's class, right. Let's therefore take a quick look at the forces. Let us say see matter, let us say we talk of me as a body, I am electrically neutral. Maybe you rub me very hard, remove some electrons from my surface, my body I say becomes positively charged, I get a charge q which I say could be positive. In fact, we must remember the charge whenever we have, maybe I have a tube, let us say I have a tube containing let us say oxygen gas. Oxygen gas if very dry and it is pumped at high velocity through a particular tube, it is quite possible that since the gas is dry and the oxygen consists of an atom which is electrically neutral, maybe by the rubbing action on the wall I could even ionize or I could give some charge to the oxygen, and it is quite possible that the surface could also become charged because it is getting conducted, and I could get a spark in this, and these are some things which we have to keep in mind. Therefore, let us not get into those details. All of us know in a dry climate if we wear a nylon shirt and we remove it, sometimes it is charged and we hear some discharge taking place. So also yes, an electrically neutral body or any substance could either get charged, and if I remove an electron from the body, well, it becomes positively charged. If I donate an electron or remove a positive charge, it becomes negatively charged. Therefore, are there some laws which govern the forces between charged bodies, and all of us have studied this in physics in our high school days. Maybe you say Coulomb's law, and Coulomb's law is very similar to the law of gravitational field or the universal law for attraction of forces, and Coulomb's law is something like force is equal to some constant into the product of the two charges divided by distance squared. This was formulated by Coulomb, which bears his name, and it is possible to derive this law, but let us try to get some feel for this. We say if you do a series of experiments or if you derive it, the value of k works out to be 9 into 10 to the power 9, and now I should have some units for charge. The unit for charge is again Coulomb C, and therefore all what I say is two like charges of the same q1 and q2 will repel each other, unlike charges attract each other, therefore we will not put any sign over here. Other than that, say force is equal to Newton divided by R is in meter square divided by Coulomb square, and this is the value of k, and this tells us the attraction between or repulsion between two charges q1 and q2 whose charges are q1 Coulomb and q2 Coulomb. This is fairly clear, and this is what we studied as Coulomb's law earlier, but I am more interested in a field, I am more interested in a force. Therefore, we look at this expression in a slightly different way, and people especially in physics they try to express this constant in a way wherein I can say the space can impart or hold charge, or rather k is written as 1 over 4 pi into epsilon 0. All what we are saying is I have a constant k, instead of using a constant k they put it in terms of a constant epsilon naught, where epsilon naught is defined as permittivity right, permittivity of free space. What is it I am talking? See, what does epsilon denote? The ability of the space between these two charges. Let us say I have a charge q1, I have a charge q2. The ability, that means I have q1 here, I have another body of mass m2, let us say mass m1 having q1 here, mass m2 having q2 here, they are separated by a distance r over here. We are talking of epsilon is the permittivity of the space between these bodies, that is the ability of the space to hold the charge, that means it permits something, and this is known as epsilon naught, and therefore the unit for epsilon naught, if we are going to say yes I need the units of this, it must be opposite of k, because it is 1 over k goes as epsilon, pi does not have units, therefore the unit of permittivity of free space should be Coulomb squared by Newton meter square. And let us try to put this unit a little more clearly, because Coulomb is a charge, Newton meter is work done. Therefore, I can also write it as Coulomb squared by Newton meter into meter. And now if I were to again say Newton meter is the work which is done, Coulomb is the charge, and how do we define potential difference between two bodies? Work done in taking unit charge from a lower potential difference to a higher potential, that is the work done in taking unit charge from one potential to the other. Therefore, I can write voltage as equal to work done in taking unit charge, and therefore, I can write this equation epsilon 0 permittivity of free space as equal to Coulomb divided by work by voltage into voltage is the potential difference, volts we say is the potential difference, and that is the work done in taking unit charge from a smaller potential to a higher potential, which is V volts higher. And when I say charge by potential is the capacitance farad, it is farad divided by meter. Therefore, what is it we see? The force is given in terms of the permittivity, that is the ability of the space to hold the charge in terms of epsilon 0 and product of the two charges divided by r r 0. Therefore, let us summarize it on this side. We say yes, I define permittivity of free space in terms of farads per meter, and this the value of permittivity of free space is going to be 1 over 4 pi into 9 into 10 to the power 9 farads per meter. This is the value of epsilon naught. But this is free space what we are talking of. If I have a space which is different, like I have maybe some air, some moisture, so all these things are available, I say the permittivity of the particular space is equal to the relative permittivity into epsilon naught, and therefore I get the value in farads per meter for any space between two charges q1 and q2. We will keep this in our mind, because when we do a problem we must be able to relate the problem. Maybe in vacuum I use the permittivity of free space, in medium in which I have something else I have to use relative permittivity. This is just a number which says how much more is the permittivity of the particular medium compared to the permittivity of free space. But I was interested in something else, not really in permittivity, but permittivity is a basic thing whenever we talk of and this is for free space. Whenever we talk of maybe attraction due to charges, we must keep in mind, yes, I have 1 over 4 pi epsilon 0 q1 q2 by r square. The only reason why I tell this in this form is we are used to studying Coulomb's law as F is equal to a constant into q1 q2 by r square, and therefore I thought maybe through the constant I must come to the value of the permittivity of free space. Well, this is one side of the story. Let us now try to still see whether I can get something for as a field or something coming over there. What is it we say? Force is equal to, again we keep this as k into q1 by r square into q2, or rather now I am telling myself, supposing I were to put a charge q in an electrical field, I have still not defined an electrical field, in a field in which I have a charge already q1 available and at a distance r, and I say, well, this is something which tells me something like a field which is available. I put a charge there, I am sorry, there is no q square here, k is equal to q1 q2 by r square. Therefore, EQ is equal to something like a force. In other words, if I have a charge q1 and at a distance r from it, I say yes, I have the effect of this on this, and I want to express effect of q1 at a distance r in terms of a field. I say, well, my field could be u, and since force is a vector, well, field is a vector, and this is what we call as an electric field. the strictly it should be called as electrostatic field, because all what we are saying is I have a charge q1, the reference, maybe at a distance r away from it, I put my body on which I want to determine the force. I know the force is equal to q1 by r squared into the particular constant, which I call as an electric field, and strictly since this object or this charge is at rest, this charge is also not in motion, it is strictly actually an electrostatic field. It is not dynamic, it is not something which is moving. If this charge is held stationary, this charge is held stationary, the field E attracts or repels it either towards it or pushes it away depending on the sign of the field and the value of q what you have. If I were to put this down, what is going to be my unit of the electrical field? E, analogous to what I had for G. For G we said G is equal to meter per second square. What is going to be the unit for E, that is the electric field? I can write it in terms of Newton divided by Coulomb, and Newton by Coulomb, instead of that let me multiply the numerator or multiply the numerator by meter, call it as Coulomb into meter, and now I find Newton meter is the work which is done in taking a charge of C coulombs, therefore work done per unit charge is voltage, and therefore per unit charge, that means work done for taking C charges, that is Newton meter per coulomb, is equal to the work done, because per unit charge is what is voltage, that is voltage, and therefore I can write it as voltage per meter. Therefore the unit of the electrostatic field is strictly Newton per coulomb, which is can be written as Newton meter per coulomb meter, which is voltage per meter, and therefore I say that the field E, let us say the field G, field E, electrostatic field is written in terms of volts per meter, just like the gravitational field is written in terms of meter per second square, right. Therefore now I can tell, yes, if I were to put a charge, if I were to characterize an electrical field in terms of let us say E, and if I were to put a charge q in it, I will experience a force equal to q into E in the direction of the field itself. I think this is what we constitute as an electric field. Therefore what are the things we have said so far? Well, whenever we talk in terms of some charges, we talk of permittivity of the space which is in farads per meter, the force is anyway in Newton, and the field, electrical field, is in voltage per meter. But whenever we talk of this electrical fields, we also know, yeah, in earth we have a magnetic field. How do I define a magnetic field? I think that also must be done, that also must be fairly well understood along with the units. How do I define a magnetic field, and in what way is it different from an electric field? Any guesses on that? See, all of us have studied this, but maybe several years ago. How would you define a magnetic field? See, after all of us when we have studied with magnets, maybe north and south, we know maybe some field is associated which we call as a magnetic field. All of us also know on the earth there is something like a magnetic field which is available. How do you define it? There must be something like a field. A field should have units. A field must have something, it must be a vector because there is some changes taking place. How do I define a magnetic field? See, there are certain things, we have done this experiment. Supposing I put a dipole here, we know the dipole, it does not really move. Supposing I put another magnet here, it aligns itself along the field, this I know. Like I put a compass over here, the compass needle does not go along this, but compass needle aligns itself along the field. If I put the compass here, well, the compass shows that, that is a dipole aligns itself along the magnetic field, that part is clear. But how do I define a magnetic field in contrast to the electrical field which we just talked of? Like for instance, again it could be a region in space, any region maybe, or over here I consider a magnet here, I have a magnetic field here. Now if I were to put a charge here, there is no change, the charge does not experience any force, but where the charge going to move in some particular direction, that means a region in space in which, let us say, a charge q experiences no force when at rest. If I were to put a charge here, well, I do not see anything, but if the charge were moving, then it experiences a force, then that field is known as a magnetic field. Therefore, let us say a magnetic field is defined as a region in space wherein in that space if I were to put a charge and that charge experiences no force when it is at rest, and what is the force it experiences when it is at rest? That is the electrical field, but if the charge were to move in the particular field, it experiences a force, then that is known as a magnetic field. Let us try to understand it a little more through an equation, because that makes it simpler. In other words, I have something like a force coming, and this force comes when the charge q moves with a certain velocity, and the direction of the force is normal to the direction of motion and also normal to the direction of the magnetic field, which I denote now by B. In other words, if I have a field which is maybe like this, and if I were to move the charge in this particular direction, well, I have a force which is coming either out of the board or inside the board, or rather I say that the thing is curl of this vector, curl of these two vectors, I have a vector cross product over here, and this is what is known as a B is then known as a magnetic field. This particular equation which defines the force in a magnetic field due to motion of charge in it is also known as Lorentz equation for force. Just like we have the Coulomb's equation for electrostatic forces, this is for forces in a field. Therefore, what is it we are telling? Well, I have something like a force which comes because a charge is moving, and when the charge is moving in a magnetic field, well, I get a force over here, or rather I have a product of qv and this. Therefore, what should be the unit of the magnetic field? How do you say the earth has so much magnetic field? Therefore, I have to now take the values. I say F is in Newton, Q is in Coulomb, velocity in meter per second square, well, this must be the unit of B. How can I express it? Can I simplify it and put it in a way which is easy for me to understand and interpret? Well, I say Newton per Coulomb into meter per second. I write it as, let's write it down here, Newton second by Coulomb meter. Can I put it in terms of something? I find that Coulomb is charge, second is time, Coulomb per unit time is what is current, ampere, and how is ampere defined? Is the current which is the dc by dt, or ampere is the current per charge per unit time, and therefore I can write it as Newton per ampere meter, and Newton per ampere matter is called as Tesla, and therefore the unit for the magnetic field B is Newton per ampere meter, which is known as Tesla, and therefore we say, well, the magnetic field is expressed in terms of Tesla, which is Newton per ampere meter. I think we should get units clear, because whenever we have to calculate some forces, we have to use units, or rather I do not even mind if you use a unit like Newton per ampere meter, but we must get a feel for these numbers. What is the value of the magnetic field on the surface of earth? It is something like 5 into 10 to the power minus 4 Tesla is the field here. We talk of maybe magnetically levitated trains and all that. We say yes, I have rails in which are magnetically levitated, and the above the rail the train is going up in air with some gap and all that. You have very strong magnetic forces of the order of a few Tesla. Therefore, we say this is a weak magnetic field of the order of 5 into 10 to the power minus 4 as is on the surface of the earth. Now, the last thing which we have to think in terms of units is, before we look at the propulsion part of it, is how do I define a field? See, after all, a piece of iron gets magnetized easily, a piece of copper does not get magnetized like what iron gets magnetized. Therefore, what is it we must, can I say something like I have permittivity of free space? Can I define some quantity, let us say Q, which will take care of the magnetic effects? Rather, we say a substance is more prone to magnetization, we call it as permeability. What is permeability? Let me repeat again. The ability of a body to get magnetized in a magnetic field. Iron gets easily magnetized, some bodies get easily magnetized, air does not get that easily magnetized. Therefore, we call it as permeability, and it is denoted by mu. And permeability of free space is denoted by mu naught, and using basic quantum physics it can be shown that mu 0 is equal to 1 over velocity of light in vacuum c naught square into something like the permittivity of free space, because electrical and magnetic fields are related in some way. It comes through the relation, the velocity of light in vacuum, which is equal to 3 into 10 to the power 8 meters per second, and we have already calculated the value of permittivity of free space. I can calculate the permeability of free space, and using this permeability for any substance I define the relative permeability mu r in the same way as I defined the relative permittivity of a body, and I say mu r into mu 0 is equal to permeability of the body, just like we say permittivity of space or permittivity of something is equal to permittivity of free space into the relative permittivity. Therefore, we can get the value of this. We know C is equal to C naught, that is in vacuum speed of light is 3 into 10 to the power 8 meters per second. We already calculated this as 1 over 4 pi into 9 into 10 to the power 9. I can get the value of permeability of. You are correct. I should have written it as meters per second. The velocity of light in vacuum is 3 into 10 to the power 8 meters per second, 3 into 10 to the power 5 kilometers per second, 3 into 10 to the power 8 or 3 into 10 to the power 10 centimeters per second. You are right. Therefore, let us get how will I define the units of permeability? See, because units are important, without units we cannot do a problem, or we will not be able to understand something. Therefore, let us say the unit of mu naught is equal to 1 over c naught square, 1 over meter square by second square. And what was the unit of permittivity? We already, I think, wrote it here, farads by meter, which was equal to, let's put it down first, farads per meter. And now I simplify this, I bring second square on top, meter over here, meter square over here. And what was farad? Farad is the charge per unit voltage, C by V. And what is V? V is the work done, Newton meter. Therefore, I have work done, that is charge per voltage that is I get the value here, but when I say farad, farad is equal to charge, that is Coulomb, by voltage, voltage is equal to Newton meter per charge over here, I get Coulomb square over here. Now let us be very clear, we found farad is equal to charge by voltage, voltage is equal to work done per unit charge, and therefore the unit of farad should be c squared by Newton meter. This is equal to meter square from here, I had already taken this over here, and therefore I cancel this over here, and therefore now I get meter, yes, meter also goes off, meter square, this becomes no, let us do one at a time, yes, meter square goes off, and this is equal to Newton by C by S square, or rather this becomes charge per unit time, unit second is equal to Newton by ampere square, and this is what is the unit for permeability, Newton per ampere square, and this is also denoted by Henry per meter. In electrical engineering they are denoted by Henry per meter, and therefore now I add the permeability units, permeability of free space, which is written in terms of mu naught as units of Henry per meter, or rather it is also equal to Newton per ampere square. I think if we are clear about whatever we have learned so far, it will be possible for us to find out, yes, this is the force, this is the thrust, this is how we calculate in engineering. But you also know, see, we always talk in terms of induced field, we talk of induced magnetic field, and we also talk in terms of a magnetic field produced by magnets itself. What is the difference? Whenever I have a charge, let us say a charge so much Coulomb per unit area, it is moving with some velocity v, that means I have a charge which is moving with some velocity, then it is possible that this produces a particular field which we call as an induced field. In some textbooks it is denoted by H, but we will see what is the unit of this before we put the value down. All what we are saying is, it is not necessary that only a magnetic can produce a magnetic field. We always talk in terms of electromagnetic field. It is also possible that the motion of charges can produce a field which we say is an induced field, and an induced field is defined as, we have to talk in terms of permeability into something like the motion of electrons, which is equal to, let us say, Coulomb charges which is moving per into velocity, charge Coulomb per unit area meter square, moving with a velocity meter per second. And now if you see the unit of this, it will again come to the unit of Tesla. Therefore, whether the field is induced by electrical charges which are moving per unit area, that means per unit area I have charge which is moving at a velocity, that also gives me the net field in Tesla. Therefore, the field due to the magnetic or due to induced field can be described in terms of Tesla Newton per ampere meter. Therefore, what is it we have done so far? Let us take a quick quick review of what we have done, so that we can now go to the problem of how to use these forces. We just say, analogous to the gravitational field G, I can also have electrical field E whose unit is voltage per meter. I can also have something like a magnetic field whose unit is Tesla, and this Tesla is something like Newton per ampere meter, and I can use the electrical field E, I can use the magnetic field B, and this magnetic field can also come from the induced field due to the motion of the electrical charges. And this is all what we have said so far. Now I would like to use the electrostatic field E and the magnetic field to be able to generate a particular force. Therefore, can I go to the next step? This is all a brief review of what we must know relating to the fields and also something relating to permittivity and permeability. Permeability is something which induces magnetic properties in the medium, that means we say it is something which induces a magnetic field. Permittivity is something which holds or which can contain charge in the space. This is the definition. Having said that, let us now come back to our story. Maybe we need to look at propulsion. Maybe force, we say yes, force is equal to m dot Vj. Now all what I am trying to say is, well, I have a charge q, it could be positive or negative charge. If I can move it or accelerate it through Vj meter per second, and if the mass of this charge the mass of m kg is to be accelerated to a velocity of Vj meters per second. Therefore, the kinetic energy to be given is equal to m into Vj square divided by 2. We can write this value. We would like to relate this value to the electrical field. And how do we define an electrical field? We define the electrical field E as volts per meter, or if I have it in a particular distance, let us say x, the potential difference is, let us say, V volts, then I can write the electrical field E as equal to V volts divided by x is so much volts per meter is the electrical field. In this electrical field, if I put a charge and I accelerate the charge of mass m, the charge being q, I am able to accelerate it through Vj, and I am interested in expressing a relation between the electrical field and the kinetic energy which I am supplying to the particular charge of mass m. How do we define voltage? To be able to do that, I would like to take a look at the definition of volts again. We define volts V as the work to be done to carry a unit charge through a potential difference of V. What I am trying to say is, the work is done by the charge of mass m having a charge q, which is getting accelerated by the electrical field, and the electrical field is given by V by x. Now what is the work which is done by the electrical field? I have work done by the electrical field. What does it do? It takes a charge of q through a potential difference of V, and potential difference V volts is defined per unit charge what is the work done. Therefore, work done by charge q, qV so much joules is what is the work done by the electrical field. The energy which the body gains or the work done on the charge is m Vj square divided by 2, and I equate these two expressions to be able to determine the value of Vj. Let me put it together, or rather I get half m into Vj square is equal to qV, or rather I get the value of Vj is equal to under root 2 qV by m, my equation 1. And what was my equation for the thrust F? F is equal to m dot into Vj, and this I can write it as m into I divided by q into the value of Vj, which is equal to 2 qV by m over here, or rather this becomes equal to I take it outside, m comes on top, q comes at the bottom into under root. What is it I get? I get q comes at the bottom into 2 V into m is equal to the thrust, and this is the thrust what I get by moving a charge in a medium. In other words, if I need a propellant to be able to do this type of job, I need, for any meaningful thrust, I need the mass of the propellant must be large, Otherwise if I have a very small mass I get a high jet velocity, but ultimately the thrust what I get is going to be very small. Therefore the requirement of my propellant, if I were to generate a force using this particular charge and voltage as it were, will be large, or I need a large value of current, or I require the charge for a given mass should not be very high. Let us try to take some look at some properties of the propellant what I would require. Just like we said a propellant for chemical propulsion should have low molecular mass, should have high temperature. So also let us try to see, let us say hydrogen has a molecular mass compared to other substances, let us say hydrogen atom has 1. Maybe I take drastically mercury has around 200. I take another substance cesium, I will say why I am choosing this a little later, 133. I take an inert gas like xenon equal to 131. All what I am saying is with reference to hydrogen as 1, the mercury atom is 200 times heavier, cesium atom is 133 times heavier, and xenon, and if the value of the hydrogen atom, if the mass of the hydrogen atom, the mass is equal to 0.167 into 10 to the power minus 26 kg, I can calculate the mass which is 200 times something like 0.33 into 10 to the power minus 24 minus 24 minus 24. We find that the molecular mass of certain substances like mercury, cesium, xenon are very much higher, and we would like to use such substances in the case of electrical propulsion or electrostatic propulsion, in which I am using force derived from charge into potential difference. Therefore compared to chemical propulsion wherein I need a low value of molecular mass, I am looking at substances which have higher molecular mass. Therefore if I were to use, maybe let us say we have still not described what the propulsion system will comprise of, we know, but we know more or less I have to first take a substance like a propellant, I have to convert the propellant into gas or maybe make it charged in some way, then I have to put a field over here, that means a voltage difference here, a potential difference which will give it a velocity, and maybe put such a potential difference such that I get a high jet velocity, and this is what gives me something like a electrostatic propulsion. But we have to see how I get it, all what I am saying is I have a propellant, I have to convert the propellant into a charge, I have to acquire the charge here, I put a field E here, so much volts per centimeter, and which gives me the value of force is equal to the thing into the charge over here. Therefore if I were to consider this, all what I am saying is I will be better off using heavier substances like mercury, cesium, xenon, and all these three have been used earlier. Mercury is a liquid metal, but its vapor is something which is dense, and when it is used in spacecrafts it coats the surfaces of spacecrafts and causes contamination, whereas cesium is a little reactive, even though it can be easily ionized, it is more difficult to use, and the general trend today is to use xenon, which is a noble gas. Where do we use xenon in real life? Maybe we see these hoardings which have some colorful display and all that, that is noble gas xenon. Therefore we use xenon in the case of propellants, but cesium is also used, and in the older electrical propulsion systems mercury is also used. Therefore what is it we are talking of? We are telling ourselves, well, the electrical propulsion system using electrostatic principle we generate ions, and how do we generate ions? We have some material like tungsten, molybdenum, what they do is when you heat these metals, these are known as low work function metals. When you heat it, it gives out the electrons. When it gives out the electrons and you have this medium like xenon gas surrounding it, when it hits a xenon neutral atom, it dislodges one more electron from it and it gets positively charged. Therefore, it is easy to make use of, you heated tungsten, you put a tungsten here in a medium of xenon or something, and it is possible for you to get charged particles, positively charged particles of xenon coming over here. At this point in time, I must also tell you, we talked in terms of the molecular mass of the particulates or the gas or the propellant used for electrostatic propulsion to be large. Now, should we use protons, should we use positive charges, should we use negative charges? The mass of a proton is about 1850 times the mass of an electron. In other words, the proton is very much heavier than an electron, and therefore, it is desirable to use the proton rather than an electron to generate thrust. And therefore, when we talk in terms of ion propulsion, basically what we are talking is in terms of electrostatic propulsion. I will continue with this in the next class, but all what we did in today's class was, we reviewed the units which we should be using whenever we talk of electrical fields and magnetic fields. Then we went to the step of trying to derive what must be the force which we can derive in a field which is electrostatic field. We find force is given by this. We find that the mass of the charge must be significant, and for the mass of size of the charge to be significant, it is necessary to use an ion rather than a negative charge, an electron, and that was the reason. Even when we talked in terms of maybe early in 1900, when the rocket equation, Tsiolkovsky made the rocket equation, he also talked in terms of electrical propulsion, but he wanted to, at that time they were making these tubes and all that, the mobility of electrons was known. They tried to make use of electrons for propulsion and found that you are not able to get force. But the moment you start using ions, namely positive charges, it is much easier to get a force from it, and we will continue on this with the next class. We will look at the type of system what we have and how it generates the force, and we will see the problems involved in it, and this is all what we will do in the next class, right. Well, thank you.